In my Structural Engineering Made Simple series, today I talk about the slenderness effect in design of reinforced concrete columns. Please take a moment and read the disclaimer at the bottom of this slide before we continue. Reinforced concrete columns are considered as slender members under an application of an axial load and two bending moments as shown. The applied forces are an axial load P sub u, a bending moment mxu about xx axis of the cross section, and the bending moment myu about yy axis of the cross section. The xx axis constitutes the axis about which the major bending moment applies. Please notice that the subscript u indicates factored internal forces, which are sometimes also called design forces, while subscript n refers to the nominal values of moment and axial load capacities. The applied internal forces are obtained based on structural analyses, applicable load combinations and load factors, and any adjustment because of the length or slenderness effect. In this video, the procedure for adjusting design bending moments for the slenderness effect is covered. For checking a column design for a combined effect of biaxial moments and axial load, and the procedure for computing nominal resistances MNX, MNY, and PN, please see lessons 5 and 6 of my series on Structural Engineering Made Simple. These are the pertinent references used in the preparation of this video. Types of structural frames. Two types of frames are recognized for column slenderness effect analysis. These are no sway frames designated by NS and sway frames designated by S. No sway frames are those that are generally prevented from lateral movement, interstory drift, or their lateral movement is within a prescribed limit. In practice, this will be the case when the lateral forces from wind, earthquake, or horizontal soil pressure are resisted by shear walls, a core, or bracing. Sway frames are subject to drift. These are usually moment frames that need to resist lateral forces in addition to the gravity loads. Let's examine these two types of frame systems. This is a no-sway frame under gravity load without interstory drift. The deformation of this frame is shown with red lines. While this is a sway frame under lateral load with interstory drift shown at the upper level as delta 0. Please note that the designation of no sway or sway frame is based on the interstory drift, and as such it is possible that a frame may be designated as NS in some but not all stories. In a building, frames in one direction may be sway, while in the perpendicular direction the frames may be no sway. According to ACI 2014, columns and stories in frames can be considered as in no sway frames if one of the following two conditions is satisfied. The increase in column end moments due to second order effects is less than 5% of the first order end moments. The parameter Q, which is called the stability index, is less than 0.05. Let's see the equation for the parameter Q. Q is equal to sigma Pu delta 0 divided by Vus L sub C, where sigma Pu and Vus are the total factored vertical load and horizontal story shear respectively in the story being evaluated. Delta zero is the first order relative lateral deflection between the top and the bottom of that story due to VUS. L sub C is the length of the compression member measured center to center of the joints. The term sigma Pu delta zero is a secondary moment developed because of the lateral displacement of the column, which is sometimes called the P delta effect. While the term VUS L sub C is the moment from lateral forces. This is the primary moment. Therefore, the stability index Q is the ratio of the secondary moment to the primary moment. Let's look at an example. Consider the following frame. This is a sway frame, and the interstory drift on the upper level is delta zero. From structural analysis, we find out delta zero is 1.58 inches for L sub C of 13.5 feet or 162 inches. These are the applied forces. Pu1 is the same as Pu2 is 24.5. Horizontal forces Fu1 is 8 kips and Fu2 is 10 kips. Therefore, sigma Pu would be 49 kips. And plugging those into the equation for Q, we find out the value of Q. Please notice that VUS would be equal to 8 kips. That's the shear for the upper story. The value of Q is obtained as 0.06, which is larger than 0.05. Therefore, columns in the upper level are part of a sway frame system. Basic considerations in computing the slenderness effect. For concrete columns, the significance of the slenderness effect is considered through advanced computer analysis using software with capability to account for the buckling effect and second-order analysis, or by using a magnification factor for the column moment. The slenderness effect can be neglected in the following cases. In columns that are non-braced, in other words in sway frames, KLU divided by R is less than or equal to 22. In columns that are braced, in other words in no sway frames, KLU divided by R less than 34 plus 12 multiplied by a ratio of M1 over M2 and KLU divided by R less than 40. The ratio of smaller to the larger end moment is M1 over M2 that appears in the equation. It is taken as negative if the column bends in a single curvature and positive if the column bends in a double curvature. We're going to examine this again later in this presentation. If bracing elements resisting lateral movement of a story have a total stiffness of at least 12 times the total lateral stiffness of the columns in the direction considered, the columns within the story are treated as braced against side sway. In the foregoing equations, R is the radius of gyration of the cross section, which is equal to 0.29 times the dimension in the direction stability is being considered for rectangular columns, and is equal to 0.25 times dimension of the circular cross section. L sub U is unsupported length of the column, which is generally L sub C minus beam or floor thickness, and K is the effective length factor, conservatively taken as 1 for no sway, and is larger than 1 for sway frames. We're going to examine the values of K later. A question is, how is the second order analysis done? A computer software capable of allowing the formulation of the stiffness matrix with a consideration for the buckling effect of the individual columns is needed. Such analyses are possible through an extension of usual finite element software to account for this effect, which constitutes a nonlinear behavior. Alternatively, the second-order analysis for sway frames can be done using the magnification factor used for no sway frames, as explained later in this video. Notice that using this method, we will be applying the magnification factors in two stages. Procedure for considering the column length effect for no sway frames. The design moment at the end of the column is designated as M1 for the smaller moment and M2 for the larger moment, where M2 is larger than M1. The magnified moment M sub c is M sub c equal to delta times M2. The magnification factor delta is larger than 1 and is equal to C sub m divided by 1 minus P sub u divided by 0.75 P sub c. The parameter C sub m is equal to 0.6 minus 0.4, the ratio of the M1 to M2. And as we discussed before, for columns without transverse loads applied between the ends, the M1 over M2 is negative if the column bends in a single curvature, as you see in that figure, and positive if bends in double curvature, as you can see in the figure to the right. For columns with transverse loads applied between supports, C sub m is taken as 1. In the foregoing equation, P sub c is called the critical buckling load and is equal to pi squared EI effective divided by KLU squared. As indicated in this case, the parameter K can be taken conservatively as 1, and for EI effective, we have three equations we could use. The first equation is 0.4 ECIG divided by 1 plus a parameter beta DNS. We're going to introduce these parameters in the next slide. Or we can use 0.2 ECIG plus ESISE divided by 1 plus beta DNS. And finally, the third equation is EC times I divided by 1 plus beta DNS. When I is equal to this equation bounded by the two upper bound and the lower bound values. Generally, when the cross-sectional area is known and we know the arrangement and the amount of reinforcement, this second equation would be the one to use. However, the first equation could be used always as an approximation. E sub c and E sub s are the moduli of elasticity of concrete and steel respectively. Ig is a gross moment of inertia. ISE is a moment of inertia of the steel bars. The parameter beta DNS is the ratio of the maximum factor sustained axial load to the maximum factored axial load associated with the same load combination. For example, if only live and dead loads are used, beta DNS would be 1.2 DL divided by 1.2 DL plus 1.6 LL. M2 in the equation for Cm has to be at least equal to the minimum value. The minimum value for M2 is Pu divided by 0.6 plus 0.03H. The multiplier 0.6 plus 0.03H would be in inches. If M2 minimum is larger than M2, Cm needs to be taken equal to 1 or calculated based on the ratio of the end moments in 1 over M2 using the equation given for Cm. Procedure for considering the column length effect for sway frames. For sway frames, the magnification of the moment is done in two stages. First, it is done for both M1 and M2 moments using a magnification factor delta S as explained later. Then the second order effect is considered using a procedure similar to what was discussed for no sway frames with a magnification factor delta. The magnification using delta S is as follows. M1 is equal to M1NS plus delta S M1S, and M2 is M2NS plus delta S M2S. Please note that while for column design we use M2, which is larger of the two moments, we still need to use the magnification factor for the smaller moment also, smaller moment, because the magnified M1 will change the distribution of the moments at the joint, which result in changes in the moments of the beams and other columns joined at each end. Now in these equations, M1NS and M2NS are the moments from the forces that do not cause sway. That's what the term NS is used. While M1S and M2S are moments from forces that do cause sway. And of course, delta S is a magnification factor. So please notice that we have to do the analysis separately for two sets of forces to get those moments. Now let's look at the parameter delta S. Three procedures are suggested for computing delta S. Delta S can be taken as 1 divided by 1 minus Q. Parameter Q was introduced earlier. This equation can only be used if delta S is not exceeding 1.5. Please notice that the minimum value for delta S is 1. The second equation is 1 divided by 1 minus sigma Pu divided by 0.75 sigma Pc. Again, minimum is equal to 1. And finally, based on a second order elastic analysis. Please note that sigma Pu sums all the axial loads in the story level. So for example, if we are looking at the design of the exterior column, the sum of all axial loads in that story level is used in computing the magnification factor. The same is applied to sigma P sub C. The reason we do this is that when lateral loads apply, all the columns in the story level contribute to the stiffness of the frame system. Usually, the second equation is the one which is used. The effective length vector K for sway frames is larger than 1 and is computed through the alignment chart based on the ratio of the stiffnesses of the columns to those of the beams at the ends of the column. This is what we call the alignment chart. Psi A is the relative stiffness at the end A of the column. Psi B is the relative stiffness at the end B of the column. The middle vertical line shows different values of K. The relative stiffness is computed through the equation given, sigma EI over L sub C for columns, divided by sigma EI over L for all the beams joining at a particular point. We refer sigma to the summation of stiffness terms. L is the beam center to center length and L sub C the column center to center length. If an end is fixed, we use psi equal to 1. If it is hinged, we use 10. In computing the relative stiffnesses, the moment of inertia of each column is taken as 0.7 Ig and for beams is 0.35 Ig. It is noted that for factored lateral load analysis, ACI allows using I equal to 0.5 Ig for all members for calculating I, or we can use a more detailed analysis, considering the reduced stiffness of all members. Let's look at an example. Compute K factor for a sway frame for the columns AB and BC shown in this figure. Each column is a 14 by 14 inch cross section. Beams are 14 by 32 inch in cross section. And the NC is hinged. Notice that at point A, there is just one beam and one column involved, while at point B, we have two columns and one beam involved. Assume the same concrete material is used for beams and columns. The modulus of elasticity E is the same and thus can be cancelled out from the equation for the relative stiffness. Using 70% of Ig for the moment of inertia of the column, we get 2,241. And we use 35% of Ig for each beam. We use the moment of inertia of the beam as 13,380. We compute psi A considering that there is just one beam and one column involved, while psi B involves two columns and one beam. And of course, psi C is 10 because we have an hinge end. So here is our alignment chart again. We mark psi A on the left line, psi B on the right line, draw a straight line connecting the 2 points. Wherever this line intersects the middle line, that's where the K value is, which in this case is 1.13. Now if we mark psi C on the left line, which is equal to 10, connecting to psi B, the intersection is at the point when K sub BC is located, and that's 1.8. The values for K will be slightly different if we assume 0.5 Ig for all members for factored lateral load analysis per ACI. Recalculating the moments of inertia, in this case we would have 1,601 for column, 19,115 for beams. Psi A, psi B, and psi C are written in here. And we can show that KAB is about 1.1 and KBC is about 1.7. In computing the critical load P sub C for sway frames, we use EI effective equations provided earlier, except that the parameter beta D and S is substituted by a new parameter beta ds, where beta ds is usually equal to 0 because we are considering lateral loads. And lateral loads due to seismic and wind load are transient load, or they called short duration dynamic loads, and for which beta ds is taken as 0. In rare situations, when the lateral load is sustained, such as the case of earth pressure, beta ds is the ratio of maximum factor sustained shear within a story to the maximum factor shear in that story associated with the same load combination. Let's look at the second order effect. Second order effect for sway frames is considered along the length of columns using the equations used for no sway frames, except that Cm is calculated using M1 and M2 computed for the sway frames as explained earlier. Therefore, the design moments would be the smaller moment MC1 is delta multiplied by M1 subject to the minimum value, and MC2 is delta times M2, again subject to the minimum value. As you recall, in the case of no sway frame, the magnification factor was delta. This is a factor now is used for this second magnification. Delta is Cm divided by 1 minus Pu divided by 0.75 P sub C. And Cm, if you recall, is equal to 0.6 minus 0.4 M1 over M2. Please notice that this magnification will only use PC for the column that is being considered for which K is equal to 1. We do not use summation of all the columns in this story level. ACI has a limitation. The moment with second order effect cannot exceed 1.4 times the moment from the first order analysis. In other words, MC2 must be less than 1.4 M2. Otherwise, the design will need to be revised. That column will not pass the design, and in this situation, we must change the design of the column, perhaps use a larger cross-section. Let's look at an example. A three-story sway frame is shown. Column AB is being analyzed in the plane of the frame. The cross-section of the column is 12 by 12. Number 8 bars used with number 4 ties. This is a tied column. And all beams are 12 by 18 inches. And all the other columns have the same cross-section. Material properties, a prime sub C is 4,000 psi, Fi is 60,000 psi. A preliminary structural analysis has shown the following moment values at the ends of the column. The analysis has been done for factor transient lateral loads, and as such, beta ds is 0. At end B, we have the larger moments. MUNS is a factored moment from forces that do not cause sway, and that's 16.7 foot-kips. MUS is factored moment from the forces that cause sway, and that's 14.7 foot-kips. At end A, MUNS is factored moment from the forces that do not cause sway, and that's 1.6 foot-kips. And MUS factored moment from the forces that cause sway, and that's 1.7 foot-kips. And the axial load factored is 186. For the second magnification factor, we also need beta DNS. The analysis shows that for this load combination, the maximum factor sustained axial load is 89 kips, while the maximum total factored axial load is 186. Therefore, when we apply the second order effect for the sway frame, we use beta DNS as 89 divided by 186, which is 0.48. Let's look at the solution. First, we need the factor K. Again, we use the alignment chart. Use 70% of IG for the moment of inertia of the column cross-section, 35% of IG for the moment of inertia of the beam. We plug the values for psi A and psi B, and remember that in this case, at point A and point B each, we have two columns and one beam joining. We get 1.9 for psi A, 1.7 for psi B, draw the straight line, and we read the K value, which is 1.52. Furthermore, the gross moment of inertia for the column is 1,728, and the modulus of elasticity of concrete is 3,605,000 psi. We're going to use the first equation for EI effective, which is the approximate and simplest equation of the three, and that's 0.4 times E sub C times IG divided by 1 plus beta ds, and beta ds is 0. So we get 2.492 times 10 to the power of 9, and the unit is in inch pounds. The radius of gyration is 3.48. LU is 15 feet minus 18 divided by 12. 18 inches is the thickness of the beam. We get 13.5 feet. Therefore, KLU over R in this case is 78.6, larger than the limiting 22. That means the slenderness effect must be considered. And for that, we also need the critical buckling load P sub C. And notice that in this case, because it is a sway frame, we use a K value of 1.52 that we computed. P sub C is 328.6, and this is identical for both columns in that level. So now we compute delta S. Because there are two columns involved, you notice that there are the 186 and 186 added, divided by 0.75 times the P sub C added for the two columns. The answer is 4.08. So we can magnify the two moments, M2, the larger moment, 16.7 plus 4.08 times 14.7, that's 76.7 foot kips. Smaller moment is 1.6 plus 4.08 times 1.7, that's 8.5 foot kips. Now let's look at the second order analysis. In this case, we use another magnification factor. And that one is the one we discussed for the no sway frame. Delta is Cm divided by 1 minus Pu divided by 0.75 P sub C, which has to be at least equal to 1. And we plug for M1 and M2, and remember that this is under lateral load, so it's a double curvature situation. Therefore, M1 over M2 is positive. That results in Cm of 0.56. Notice that EI effective is different in this case because now we are applying the second magnification factor and we need to incorporate the beta DNS that we computed. The answer is 1.684 times 10 to the 9 inch-pounds. So this means there is a reduction in the stiffness, which is usually because of the cracking. P sub C is a critical buckling load in this case, and notice that in this case K is equal to 1, and we end up with 512.4 kips. Plugging those into the delta equation, we get 1.1. Now we apply the second magnification. So at the end, 2, M sub C2, which is a larger moment, is 1.1 times 76.7, is 84.4 foot kips. And at node 1, which is end A, is 1.1 times 8.5, which is 9.4 foot kips. So we still have to do one more check. We need to check these against the limits. First of all, the moment with inelastic effect cannot exceed 1.4 times the first order moment. That would be 1.4 times 76.7, which is 107.4. Both of these moments are smaller than this limit. Therefore, we don't have to change the cross-section of this column. And we can use the MC2 of 84.4 for checking the design. Notice that the end moment will need to be at least equal to minimum, which is Pu times 0.6 plus 0.03 H, and that would be 14.88. The moment at end A is 9.4 and is smaller than this value. Therefore, for MC1, we have to use at least 14.88 foot kips. The ACI procedure for the slenderness effect presented in this video is intended for use when a more detailed finite element analysis with consideration for the second order effect is not available. This method is straightforward and offers a simple procedure for computing design moments at both ends of a column. Please note that the final moments computed must be used to balance the moments of the beams that are joined with columns. This is done to maintain the equilibrium. Accordingly, the end moments for beams will be modified considering the column end moments. Thank you for watching this video.